Josh Zeid, who comes from our Material Science and Engineering department, will give the talk. Josh has been at UD since 2007. He earned his PhD at UC Santa Barbara, which is the home of one of the laureates, Tsuji Nakamura, who happened to be on Josh's preliminary exam committee. Josh's primary research interest is in nanoscale engineering of novel semiconductor and composite electronic materials for energy conversion and electronic devices. So Josh, wherever you are. Good.
So thank you for the introduction. I have a bit of an advantage, which is I think I'm the only person who can hold a Nobel Prize-winning invention in his hand and show it to everyone. So it gives me a bit of an advantage in terms of practicality and explanation. But I want to, So I want to thank Doug and the College of Arts and Sciences for the invitation, and also the excuse to buy a new toy for the event, which is a blue laser pointer based on the technology that won the Nobel Prize. This Nobel Prize is for the invention of efficient blue LEDs and the bright and energy-saving white light sources that they've enabled. So what I'm going to do is take this from a bit of a question and answer point of view, which is there's a bunch of questions that some of you may have about the prize, and I want to just go through a few of them. Let's start with the basics. What is an LED and how does it work? I promise this will not be a physics or material science class. It's going to just be a brief overview, but to give you some idea of what this actually is. What makes blue so special? So some of you may have seen LEDs since the late 1960s, and yet you didn't see a blue LED probably until 1994. It's kind of a big gap in time as technology goes. So what makes blue so special? Who are the laureates? What did they contribute? And the interesting thing about Nobel Prizes, especially in science, is that there's also usually a lot of other people who did a lot of important work that deserve at least some degree of recognition. So I just want to mention just a few of the many people who also deserve some recognition, which I'll do in terms of a history. How do white LEDs work? So the prize was for sort of two things, blue and the white LEDs they enable. And why is blue so important for white? And finally, the question that is sort of a key question here, why does the blue LED deserve the Nobel Prize? Especially when the red LED never won a Nobel Prize. Lots of fantastic things don't, so what makes blue so special? So I'll start with what is an LED, and I came up with a definition which some of you will find helpful, but many might not, which is that an LED is a semiconductor light source that takes advantage of a p-n junction to produce light at a wavelength determined by the band gap of the semiconductor. So before everyone is frightened, I'm just going to look at a few of these words and give you some analogies just to explain what these terms mean. What a semiconductor is, light source is pretty self-evident, and what the band gap is. So I want to start with a ladder, just something as simple as just a basic ladder that presumably someone used to put up the screen. You have a bunch of different levels on the ladder, and you could stand on any of those levels. It's more or less continuous. The spacing has to be close enough you can climb. So what would happen if some real jerk came along and just knocked out a couple of rungs of the ladder? So assuming no one was on them at the time, you'd now have this missing gap where you really could not stand. So you could stand below it, and you could have people stand on these rungs, and if you could get there, you could stand above it, although it would be a bit of a challenge, but you'd have these missing areas, these states that you couldn't be in. So the same thing is true of a semiconductor. A semiconductor is a material that has these missing states. So these green circles are electrons, magnified many, many, many times. And so in a semiconductor, you have a band called the valence band at the bottom, which is full of electrons. You have a band at the top called the conduction band, where no one is standing there, but there are rungs of the ladder. And you have these missing rungs in between, where there's no place for electrons to be, so electrons cannot be there. So what would happen if you took an electron and put it here? We know it can be there, but it's at a higher energy. It's like standing at the top of a ladder with no rung beneath you. What it wants to do is it wants to fall down to where it came from, but when it does that, that means it's losing energy, and that energy has to go somewhere, and where that energy goes is into light, which comes out of the device. And the energy of that light is determined by the separation here. So the question then is, how do you get electrons up here? Because we already said that there's no rungs on the ladder in between. How do you get an electron up here? It turns out what you can do is you can take advantage of this thing called a p-n junction, where you can add a dopant. It's not just for professional athletes anymore. It's a material that adds some impurities that has extra electrons, which you can add to the material, putting electrons here. And that's the first step you need, because you need the electrons up here, but there's a problem, which is that there needs to be some place for them to go, and all of the available places in the valence band are full. If I said, everyone get up and move right a seat, that might be a problem because someone's probably sitting in the seat to your right. So what you can do is you can make another type of material, which is what's called a p-type material, where you add a different dopant, which has fewer electrons. And so essentially, you have these things called holes, which are just missing electrons. And so these are places where electrons could fall to. Now, if you want this to work, these need to be in the same device. And so what you do is you put these together into what's called a p-n junction. You hook up a battery or any voltage source, which essentially pushes holes this way, pushes electrons this way. They recombine and give off light. So that's fundamentally how every LED works. It's a p-n junction, or every modern LED, I should say. And the light that it gives off is coming from this particular structure. So what determines the color of the light? I apologize for the figure, but this is to show you the visible range of light. So these are the energies that they correspond to, or the wavelengths. And it turns out that most of the semiconductors, the ones we work with in my group, for example, are mostly in the infrared down here. But most of the semiconductors that people typically have used for LEDs up through the 1960s and really until the invention of the blue LED are down here. They're in the red, and they sort of get into the yellow. And the first green LEDs were this aluminum phosphide, that sort of sickly green color that you may have seen. And it turns out if you want to make a blue LED, and I'll go through why you might want to, you have fewer materials to choose from. You have these 2,6 materials. Zinc sulfide is sort of the classic one. And it turns out that for reasons I really don't want to get into now, they don't make very good LEDs. And so that leaves one option, which is this gallium nitride, indium gallium nitride system, which is what turns out the blue LEDs that we see now and the blue laser diode at my pointer are made from. So why is this a challenge? So it's worth mentioning that the history of LEDs goes back quite a long way. The first work was actually 1907. H.J. Round found just a little tiny bit of light emission from carborundum, which is now called silicon carbide, as a mineral. It was first really actually understood in any way in 1927, where it was the same material, not very good or very strong emission, but by looking at it and studying it systematically, people started to get an idea of this notion of band gap and relaxation. But the first modern LEDs, as we would talk about them, were actually Bob Baird and Gary Pittman at Texas Instruments, who made an infrared LED from gallium arsenide, which is the material I showed you towards the bottom. It's worth mentioning, Michael Arnold in the last talk talked about Bell Labs and deregulation. One of the losses in deregulation were institutions like Bell Labs and corporate research at GE, RCA, IBM, all of whom were coming up with basically the same technology right around the same time in the golden age of semiconductors. But Bob Baird and Gary Pittman at TI beat them to it by just a few weeks and got the first patent. The first visible LED was Nick Holonyak, who was at GE at the time, was the first red, which was gallium arsenide phosphide. He then spent the next 50 years or so at the University of Illinois building a very strong semiconductor program there, and just recently retired. The first blue technology was actually Jacques Pankove, who was at RCA and then later at University of Colorado, who did the first gallium nitride growth with colleagues. And 1972 was the first gallium nitride LED. You can see a picture of it here. You didn't hear their names as Nobel laureates, so the big question is what took until 1994 before you had high efficiency LEDs, and what makes the LEDs from 1994 so much different from the LEDs from 1972? And it's a really interesting Nobel Prize because in some sense, at the risk of offending some of my colleagues, there's no new physics in it. It's really a Nobel Prize for real innovations in material science. You can notice that I have gallium arsenide phosphide, silicon carbide, gallium nitride. It's really about materials. So I want to start by the people who won the Nobel Prize and just a really brief introduction to who they are. I'm going to go into Shuji Nakamura in a little bit more depth as we go on. Isamu Akasaki was born in 1929 in Japan, got his doctorate in engineering at Nagoya University, and stayed there as a professor. This is actually a very traditional thing in Japanese academics, where someone will get a PhD and if they're one of the top few people, become faculty at that institution until the age of 63, which is the mandatory retirement age for faculty in Japan. Not something I would advocate, but something that is common in Japan and a few other countries, when he then moved to a private university, Meiji University. Hiroshi Amano was his student at Nagoya University, and the reputation is that he was kind of this milquetoast guy who went to the lab and wasn't really very sure of himself, but just did the work that he was told and got good results and went to his advisor, and his advisor said, yes, good, that's great. And Akasaki's reputation is very much the traditional Japanese academic with the proper pedigree and so forth. And then there's Shuji Nakamura, who worked for the Nichia company, which no one in Japan had heard of at the time. He did not, as you'll see, have a PhD at the time. I'm actually going to draw a line here because it turns out there's always a little bit of intrigue associated with the Nobel Prizes. Akasaki and Amano and Nakamura hate each other. It's going to actually be an interesting time in Stockholm in December, because apparently up until recently, they actually refused to be in the same room as each other. And the reason for this is that Nakamura has been described by a colleague as the nail that sticks up that just won't be hammered down. So I'll talk a little bit more about him and his role in this. But he's generally regarded as the father of the LED, and many years ago he had a pointer much like mine, but more powerful, and developed in his own lab rather than purchased with. I love you, sweetheart. So what did they actually contribute? So the real contributions of the Nobel laureates this year were in material science. So Akasaki and Amano were the first to really make progress. And there were a variety of problems, and they came up with solutions. So the first problem is that growing gallium nitride is really hard. It's an incredibly difficult material system to grow, and their solution was to really, after a lot of trial and error, discover that if you start low temperature growth of actually aluminum nitride barrier layer on a sapphire substrate, you can actually get decent quality of gallium nitride, much better than the stuff from the late 60s, early 70s that I showed you earlier. And so you had a high enough quality of material that you had a chance of light. The other problem is, I showed you before that you need this p-n junction to get a good LED, and it turns out making gallium nitride p-type is actually very difficult. It's naturally n-type. You naturally have too many electrons. If you put in acceptors, the things that normally take electrons, you can't get enough holes, and so it's hard to make it p-type. And so what they discovered is magnesium doping. Magnesium is not the most obvious dopant you would choose. In fact, it was one of many that had been tried. Worked well. If you then put in an electron microscope, which was something they did to figure out what was going on, and irradiate it in this electron microscope for a while, you actually got p-type material that you could use to make a LED. So this was the first reasonable efficiency gallium nitride-based LED was Akasaki and Amano, and it had a couple of problems. The first was that it was utterly impractical. Anyone who's used the electron microscope anywhere knows that it's incredibly time-consuming, expensive. A few years ago, I saw that in the history of mankind, maybe 1 cubic millimeter of material has actually been looked at in transmission electron microscopy, more in SEM, but still not very much. And what Nakamura realized is that it was very possible that what they were doing with this electron beam radiation was just getting rid of hydrogen, and that he could potentially just heat this up in an oven without hydrogen and get the same effect, and it turned out to work really well. And so he got his first LEDs, but Nakamura had a bit of a problem. Nichia, the company he worked for, underwent a change of leadership from a father to a son, and the father was content to let him do what he wanted. The son was more interested in the bottom line and said, stop working on this. It's not practical. You're not going to get a useful device. Stop working on it. I don't want to waste money on it. So he had to work kind of quickly and secretly, more or less. He went to work at 7 in the morning, went home at 7 at night, did the things that his bosses wanted, and then every free moment worked on it a little bit more. And what he found is you can actually improve the efficiency by using more materials, indium gallium nitride, which gave you the energy you wanted, and heterostructures. And so he made the first practical, as in manufacturable, high-efficiency LED in '94. And this is why he is actually frequently described as the father of the blue LED. The fact that he was a consummate showman didn't hurt much either, but he really deserves a lot of credit for that. But he broke all the rules. He is known for being an iconoclast in the world. So first of all, he didn't get his doctorate until after inventing the blue LED, and it was more or less you invented the blue LED, here's your doctorate, as long as you write everything up. He had written 15 papers while working on it without the permission of his company, published them in the US, and his bosses just didn't actually notice, it turns out. They were okay with it because he also filed patents, which we'll hear a bit more about in a second. So it was this university no one's ever heard of, even in Japan. It's essentially a couple steps above, say, DeVry. It's not a well-regarded institution. It isn't the University of Nagoya. It's rather this sort of second-rate technical school. But he did receive a bonus from his company of 20,000 yen, which sounds pretty okay until you realize it's approximately $180. So he did something very unprecedented. He sued his company that he worked for royalties. This had never happened before in the history of Japan. They had no precedent in their legal system for suing your company for royalties because it just wasn't something that was done. And the Japanese court decided the invention was actually worth 60 billion yen, or a little bit over $500 million, and awarded him 20 billion yen, or $190 million. The company, which was no longer such a small company, appealed, and they ended up settling for a mere $8.1 million. So did all right. And he landed on his feet because since 1999, he's been professor of material science at the University of California, Santa Barbara, where he, with some colleagues, established was by far the largest nitrides program at the university, and his office is somewhere right around here. So blue LEDs are nice, and it's nice to have a pretty laser pointer that's different than most of the ones you've seen, and to have something else I can hold up. But the real reason that this was a Nobel Prize winning is because blue LEDs are necessary for white LEDs. How many of you have heard on NPR or News Source that the way you get white LEDs is by having a red LED, a green LED, and a blue LED together? Did anyone hear that? So it turns out you can make a white LED that way, and in fact, this monitor in the back of the room is LED lit, and that's how it works. But the color space is awful, it's inefficient, requires complex drivers. So the way it actually works is a little bit different, and I have a little bit of a demo. What you do is you have a blue LED and you have a yellow phosphor, and it turns out that phosphors were actually one of the specialties of the Nichia Corporation. But I want to actually do a little bit of a demo, and so for the arts and crafts portion of the evening, I print out the UD logo, and breaking the university style rules, I change the colors by coloring it in with a highlighter. And so this highlighter is yellow, as hopefully everyone can see, and it's a fluorescent highlighter. And so if I take my blue laser pointer and point down the white of the page, it shines blue. And what I hope you'll be able to see is if it hits, when it hits the yellow, you get white. It's a broadband phosphor you can see in the picture. And so this gives you a much better color, maybe not so much when it's a highlighter and a blue laser. Can everyone see that? Okay. So you get a really pretty decent white light, and as some of you may have, we recently purchased the first ones. You can start buying white LEDs for your home, nearly infinite lifetime. But the reason it really matters is efficiency. So here is from the information published by the Nobel Prize Committee, sort of a history, brief history of the technology of lighting your home, starting with an oil lamp, pretty old technology. And you can see how much light you get from it. The answer is not much. So 19th century technology, Edison, the incandescent light bulb, you get 16 lumens per watt of energy. So it's essentially a measure of the efficiency. And what that corresponds to in terms of what's called wall plug efficiency, which is how much light you get based on how much energy is, or how much power is coming out of your wall, it's about 2% efficient. So actually the first blue LED was already better than incandescent bulb in terms of efficiency. Fluorescence, we have nice fluorescence here. Probably most people have switched to compact fluorescence for their home. In fact, it's getting harder and harder to buy an incandescent bulb. You get about 10% efficiency. You get 70 lumens per watt. But modern white LEDs are greater than 50% efficiency, about 300 lumens per watt. And in fact, Sora, which is a startup company founded by Nakamura and colleagues, recently reported 75% wall plug efficiency for their white LEDs. So why does this matter? The United States Energy Information Administration says that in the US, about 12% of total energy usage goes to lighting. And in fact, in much of the world, it's actually more. The only reason it's so high in the US is because or so low in the US is because we use a lot of electricity for other things. So the question is, where does this really matter? So I'm showing here a map of the world that's from NASA's Visible Earth at night. And it's essentially night everywhere. Don't ask me how they do that. It's a time lapse. And what you can see is where there's significant amounts of lighting. And you can see Europe, Japan, the United States, or especially the coast of the United States, coasts of most of the world. You more or less can't see Africa or a good chunk of South America, large parts of Asia. So where does this technology matter based on improving the efficiency of lighting? Open question. Where does it matter? Okay, so it matters in both the light places, because there we're reducing the usage of energy because we're replacing inefficient light with efficient light and reducing our energy needs. But it matters even more in the dark spots. And I have one more demo item, which came from IKEA a few years ago. It's a solar-powered desk lamp. I'm going to avoid blinding people in the front row, but it's LED lit. And this is something that's really only possible with the efficiency of LEDs, because otherwise it just wouldn't last very long. So I had the fortune in March of traveling with my colleague Ismat Shah, who's going to give the next talk, to Pakistan, to a city which doesn't quite crack the top 10 in populations in Pakistan. A pretty small city, although it's worth mentioning that this city, which doesn't quite crack the top 10, has a population larger than the state of Delaware. In the city, the power went out roughly 4 times a day? 5 times a day. At the university where we were, there was a backup generator, so 10 seconds, 30 seconds later, power would come back on. Most of the rest of the city, not so much. And if you got even 15, 20 minutes outside the city, there was no grid to go down. So education, I think being at a university, we all agree education is pretty important. In fact, if you go to the bookstore, there's a quote from the friend of the university, Bob Gore, talking about the ability education has to change the lives of people. And that's especially true of people in developing countries. But the problem is you work all day, you go to school if you're lucky, and then you come home and you want to do your homework. What do you do it with if you don't have light? And the answer is artificial lighting is a real game changer for the developing world as well as for the developed world, because it means you can then do your homework at night using the power you stored up during the day with your solar cell on your roof. So the Nobel Prize, this has been a bit of a controversial Nobel Prize because it's not fundamentally new physics, but Alfred Nobel intended the Nobel Prize to be for those who confer the greatest benefit on mankind, and I think it's easy to see that the LED light, especially the white light enables, have really done just that. So with that, I'd be happy to answer any questions you might have.
Great. Any questions from the audience? Yeah. Why don't you ask?
Hold on. In this case,
Here.
Sorry?
can you tell, how do you define efficiency in this case?
Okay, so how do you define efficiency? So there's actually lots of different ways of defining it. What I'm using is essentially wall plug efficiency. So any given energy of light has some amount of energy that's a minimum required. And so what you can do is you can compare the energy over time, which is the power from your source by measuring the brightness to the amount of power you put in. And so that's what's called wall plug efficiency. There are other forms of efficiency you can use, but that one is a nice one because it's something that we see in our power bill every month and can relate to. But this is actually, the 2.7% was the external quantum efficiency, which is essentially a measure of how many photons out you get for each electron hole pair you inject. Sorry for those for whom that might be more technical than you want.
Is there a thermodynamic limit on the maximum efficiency that you can achieve?
So this is essentially, there is, and essentially what you can do is you can look at, depending upon how you define efficiency, wall plug efficiency of 100% would mean every little bit of energy you get out of your wall goes into producing photons. In practice, you can actually get pretty close to that, but not quite. I think the limit ends up being somewhere around 80%, but I'm not certain of exactly what that is for LEDs. It's not anywhere near as troubling as something like fluorescence or incandescence, where the theoretical limit is still quite low.
Yeah. Are there other questions? Are there, what are the barriers toward getting more LEDs out into Africa, distant parts of Asia, and so on? Is this affordable to typical people living in those areas? So
there is still a cost issue, although LED prices have gone down really drastically in the past few years. So there is still something of a cost issue, and there's societal issues and just distribution channel issues. But in terms of costs, it's becoming more and more affordable to at least some fraction of people in developing countries. In places where there's no real infrastructure, it's still a bit of a challenge, but prices are going down pretty quickly.
Yeah, I remember when I was, I think, an associate professor, I bought my first red LED pointer, and about 6 weeks later, every teenager had one, you know. I mean, I paid, I think, $200 for it, and within a matter of months, it was free, essentially.
Yeah, so it's amazing how quickly they've gone down. Green has done the same thing. Blue are still a little bit pricey, about $100 still, although if you look about 2 years ago, it was about $800 to $1,000. So it's really come down quite quickly. The interesting thing is you can actually get a purple one, which looks sort of like this, but it's harder to see, for about 15 or 20 bucks. Can anyone tell me why just a 405 nanometer wavelength instead of 445 is so much cheaper? Anyone know? Okay, so you'd think that it might be the same diode they used in white LEDs, and that's actually a very good guess, and it's not far off. It turns out Blu-ray players use 405 nanometer LEDs, and Blu-ray players have come down just massively in price. They mass produce just enormous amounts of the 405 nanometer laser diodes, and so the laser pointers have come down commensurate with that. So it's really an economic issue rather than a technical issue at this point.
Right. Okay. Thank you.